Okay, chemical equations, changes in chemicals, thermochemical equation, changes in chemicals, and a change in heat. Let's try and review all of the different thermochemical equations that we saw. The first was the lattice enthalpy. And this had a very specific definition. This was the energy for 1 mole of a gas. I'm sorry, 1 mole of a salt. So I'm putting metal and X. X there is representing non-metal, although a lot of times we do use X to represent halides. So this is just generic. A salt going into cations and anions in the gas phase. Does that take a little bit of energy or does that take a lot of energy? That takes a lot of energy. We talked more about intermolecular forces, and we know that those ions are held together by ionic bonds. So to take those away and have them existing as separate species, that takes a lot of energy. So lattice enthalpy, positive, negative, or do you need some information? Always positive. This will always take energy to do. So lattice enthalpy is always a positive number. We can come back to it, but we also talked about some factors impacting lattice enthalpy. Charge of the ions, stronger charge, a larger charge, stronger attraction. Larger ions, weaker attraction, more distance between the center of that charge. We talked about this delta HD, which was the dissociation energy of a bond. Dissociating a bond, breaking a bond. So if we said something like element A bonded to element B, whether it's a solid, liquid, or gas, our thermochemical equation defines this as breaking it into gases of the constituent elements. We looked at hydrogen, H2, becoming 2 equivalences of H gas. We looked at methane, CH4, becoming an equivalence of carbon gas and 4 equivalences of hydrogen, H gas. Can't say hydrogen gas because that's assumed to be H2. So, dissociation of a bond. Positive, negative, or do we need more information? To break a bond. Put energy in, get energy out, or does it depend? Always endothermic, always requires energy because bonds exist in this energy well. That's why bonds form, is because they're energetically stable. So anytime you're going to break a bond, this will require energy. Then what did we talk about? Oh, I just realized I left my notes upstairs. We're really winging it today. We talked about the enthalpy of combustion. I think that was what was next. So this is some compound, let's call it A, reacting with oxygen. And to be fair, we don't know the actual products. If A is some organic compound, then we know that we'll make carbon dioxide, water, carbon dioxide and water. If there's any nitrogen in there, we can make nitrogen oxides. If there's any sulfur in there, we can make sulfur oxides. Any metals, we make metal oxides. So really all we know is that we're going to form some sort of chemical oxide depending on what our chemical is. Endothermic, exothermic, or do we need more information? Exothermic. Almost always. I don't know that I can think of a problem off the top of my head where reaction with oxygen requires energy. Just think of rust. Rust takes a very long time, but that is iron reacting with oxygen and releasing energy in that process. So this is almost always an exothermic process. Maybe there's some instances it's not, but I'd imagine this is almost always true. Were there any other reactions that we did? Otherwise, the rest was just, oh, I do remember. Enthalpy of formation, which we just wrote as delta HF. Actually, now I'm thinking, maybe I didn't give it to you as delta H com for combustion. Was it just delta HC for combustion? See, this is where your notes are very helpful, and mine. Delta H of formation, the standard enthalpy of formation. This also had a very specific form. And it's actually really hard to write generally. So I'm going to write it for a specific chemical. If we wanted to show the delta H of formation, the enthalpy of formation for water, we're looking at forming 1 mole of water from its constituent elements in their most stable form. So that would be hydrogen gas at its most stable form, room temperature and pressure, is diatomic hydrogen, H2. And oxygen in its most stable form is diatomic oxygen, O2. And I only need half an equivalence of O2. Enthalpy of formation, positive, negative, or do we need more information? We need more information. Sometimes the enthalpy of formation is exothermic. That process releases energy. Sometimes forming that chemical requires energy. These reactions can be endothermic or exothermic. Okay, there's that actually leaves me with an important piece about this reaction up here. When we say enthalpy of combustion, we've actually had a caveat on all of these. Enthalpy of the lattice is 1 mole of the salt. The dissociation energy is 1 mole of that chemical. The combustion energy is 1 mole of whatever is combusting. And so in this case, I would need half a mole of O2 to get to this imaginary combustion product that I've listed. Enthalpy of formation is always 1 mole of whatever product I'm interested in. So this is that caveat. This is what makes it specific and why certain equations are not necessarily standard because they don't follow that rule of having just 1 mole of whatever you're looking for. All right, and then lastly, we can use a lot of this to calculate the heat of combustion. I'm sorry, the heat of the reaction. This doesn't really have a good form either. This is just A plus B reacting and forming C plus D. Starting materials become products. Is the heat of a reaction endothermic or exothermic, or do you need more information? Need more information. These reactions, we can never quite tell. We have to calculate it. And this is what's given on your equations sheet. To solve for this value, you can sum the enthalpy of formation for the products, final, minus the sum of the enthalpy of formation for the reactants, initial. And on the equations sheet, it also has this N times delta H. That's an important feature that helps you account for the energy of formation of every mole that's needed in the chemical reaction. If the enthalpy of formation is always per 1 mole of the chemical you're interested in, but your chemical reaction has 2 moles, 5 moles, you need to multiply that heat of formation by 5. You can make sure that you do this by just watching your units. Enthalpy has what units? We like to write enthalpy with units of what? Kilojoules per mole. And I like you to describe moles of what? This is not just per mole, this is per mole reaction. And if the mole of a reaction is 1-to-1 with the mole of the chemical you're interested in, for instance, 1 mole of lattice enthalpy is 1-to-1 with 1 mole of the salt. 1 mole of heat of formation is 1-to-1 with 1 mole of the product you're interested in. 1 mole of combustion is 1-to-1 with the compound you're combusting. But 1 mole reaction is not necessarily 1-to-1 with moles of oxygen. Right? So I like you to remember that this is per mole reaction. And you can always do some stoichiometry to say, I'm looking at 1 mole of A, and there are 2 moles of A per 1 mole reaction, and this is how many kilojoules per mole reaction. Actually, I don't like to always put numbers in there. I just want to show you how to convert it. If you have some number of moles of A, and you know there's a ratio of the moles of A per mole of reaction, that's just a weird way of saying as the balanced chemical equation is written, so this is always 1, then I can figure out how many kilojoules per mole of reaction. Does the term, I know you guys have had to work hard to understand moles because it's a challenging concept. It's a huge number representing a lot of things in a much more comprehensible way. So you guys understand better when I say grab 1.5 moles of water, that I'm talking about a specific number of water molecules, and that would have a specific mass, right? Do you understand when I say per 1 mole of reactions? How many classes have we had this semester? What number of classes have we been to? About 30? Is that 1 mole of classes? Have we gone to class 1 mole times? Definitely not. Like, not even close, right? That's what 1 mole of reaction is saying. Not just you take 1 equivalence of that reaction and react those molecules together, but you do that 6.022 times 10 to the 23rd times. You repeat that chemical reaction as it's written, with however many equivalences of everything is written, 1 mole's worth of time. That's how you can get this much energy released. If you just reacted 1 molecule or just 1 equivalence of that chemical reaction, you'd get such a small amount of energy. But you do that 6.022 times 10 to the 23rd times, you get this measurable amount of energy. All right. Good review on thermochemical equations. Did that answer enough about lattice enthalpy for us, or should we look more into it? Okay. Good. Then let's look at using Hess's law to solve for the heat of a reaction. And then I think if I can find a good problem, I'll also have you guys use the heat of formation to solve for the heat of a reaction. All right, so we're going to take this reaction, 2 moles of COS decompose into 2 moles of carbon dioxide gas and a mole of S2 gas. Which requires 192 kilojoules. Also, this COS gas can react with oxygen. So I'm going to write plus O2 to give us carbon monoxide gas and sulfur dioxide gas. And this releases 265 kilojoules. I want to find the heat of the equation, heat of reaction, for S2 gas reacting with oxygen gas to form sulfur dioxide gas. A lot of you have been getting very good at this. Don't take an equation at face value. Always double check that it's balanced. Because the second you take it at face value and it's not balanced, now your conversions get screwed up and you're unable to actually solve for the right answer. And I'm sorry, I don't have a name for COS. It's probably something like, oh, I don't even want to guess. Carbonyl sulfide. It's a weird name. Yeah? Good. So this is an example with Hess's law, by the way. You guys remember Hess's law? Easy way to say it? The sum of the parts is equal to the total. That's all. Which is a very intuitive law, by the way. So if I can add together these top equations to give me what I want on the bottom, then I can do the same with their enthalpies and get what I want on the bottom. Okay, so first of all, top equation, balanced? Yes. 2 carbons, 2 oxygens, 2 sulfurs. Second equation, balanced, 3 oxygens, 1 carbon, 1 sulfur. Good. Last equation, balanced, 1 sulfur, 2 oxygens. No, I'm sorry. 2 sulfurs to 1 sulfur, not balanced. So I need to add a coefficient 2 on the right-hand side so that my sulfurs are balanced, which throws off my oxygens. Do you guys still have your accounting system to help you keep track of this if you're not quite there yet? Good. Know how to go through this nice and slow so that you can verify what you're looking at. Now I've got 2 sulfurs on the left, 2 on the right, 4 oxygens on the right, 4 oxygens on the left. Can I sum together my top equations to give me what I have underneath? COS, carbonyl sulfide on the left, plus carbonyl sulfide on the left gives me 3 carbonyl sulfide on the reactant side. I don't want 3 carbonyl sulfide on the reactant side. So this is not great. Also, S2 is on the product side, so when I sum all of this together, S2 will stay on the product side. Not great, because I want S2 on the reactant side. So if this is not the part that I want, then let me change it so that I have it in the form I want. What can I do? Flip the equation. Show the products as the reactants. 2 CO gas plus S2 react to form 2 COS gas. Perfect. delta H changes as well. This is the same value, but now with an opposite sign. What is that chemical equation trying to tell us? We were given this equation. These reactants take in energy to become these products. That was not a useful form of the equation. So we flipped it. I want to look at how these products come down to form these reactants, which means that the energy change is exactly opposite. Logical? Great. All right. Carbonyl sulfide on the right will cancel with carbonyl sulfide on the left, except only one of them would cancel on the right. So what do I do? I don't want to flip it because they're starting to cancel. They're just not canceling totally. Berkeley. Multiply top and bottom equation by 2. Multiply the bottom equation by 2, which means 2 carbonyl sulfide will cancel with 2 carbonyl sulfide. I cannot multiply just one piece of this equation. If I'm going to multiply any of it, I have to multiply all of it, and that includes the thermal part. Because if I'm now reacting with more chemicals, I should now be giving off more heat. So multiply everything by 2. I'm going to show that in orange. I'm going to add 1 times 2 is 2 carbonyl sulfide. 1 times 2 is 2 moles of oxygen. 1 times 2 is 2 moles of carbon monoxide. I really wish that there was another unit in here, another coefficient, so I could show you that you have to multiply all the coefficients. But instead, all the coefficients are 1. And then lastly, my standard enthalpy is now negative 500 and, thank you. I'm asking to react, to burn twice as many molecules. I'm going to give off twice as much heat. Yeah? And you would say the same. If you blew up a cup of gasoline, measured the heat that came off of it, and now blow up a car full of gasoline, you're going to get a lot more heat. All right, now we can sum them together and start to cancel things out. So 2 carbon monoxide molecules cancel with 2 carbon monoxide molecules. S2 cancels with nothing and comes straight down to my final reaction. 2 carbonyl sulfide on the product cancels with 2 carbonyl sulfide on the reactants of the next equation. 2 O2 cancels with nothing. 2 SO2 cancels with nothing. Saves, saved, saved. That gives me S2 plus 2O2 gives me 2 SO2. That's really important because if the coefficients didn't line up, that means I'd have to do some more multiplication or something. Something's not quite right. But all of the coefficients lined up exactly as we wanted them to. So now I take negative 192 plus negative 530. Do you have this number, Ryan? Thank you. Now I've written this as negative 722 kilojoules, but that could really be written as what? Kilojoules per mole. And when we say per mole, we're saying per mole of what? What? Per mole of reaction. And per mole of reaction is 1 to 1 with moles of S2. So we could also say this is the heat released per mole of S2 that is combusted. This is the standard enthalpy of combustion for S2, because I've got a coefficient 1 in front of my S2. So originally these were just standard enthalpies, but I can actually add this now to say standard enthalpy combustion. It agrees with my rules for standard enthalpy of combustion. Okay, what questions do you guys have on that? We had to apply both rules, your ability to flip equations and your ability to multiply equations. That was an important skill. Sometimes you don't have to do either of that. Sometimes the equations as written sum together to give you exactly what you want. Sometimes you have to flip both equations. Sometimes you have to multiply by a fraction, right? Sometimes you have to multiply this by 1/2 in order to have the coefficients that you want at the bottom. Okay, any questions on it? Can you say that one more time?
Yeah, so when we have to use a fraction, is it the same concept that we use
No. No, what I meant was, what if the equation down here has smaller coefficients than the equations up above? Actually, you know what? I could have actually phrased this another way. We said that we wanted to cancel carbonyl sulfide, so I needed 2 moles of carbonyl sulfide to cancel 2 moles of carbonyl sulfide. But I could have also multiplied this top equation by 1/2. So that 2 moles of carbonyl sulfide becomes 1 mole, and 1 mole cancels with 1 mole. That would be multiplying an equation by 1/2. So 2 would become 1, 2 would become 1, 1 becomes 1/2, which is not ideal because I don't want 1/2 mole of S2, but I could have multiplied the top equation by a fraction and then also multiplied the heat by 1/2. So that's what I meant. When we multiply by a fraction in solving a balancing problem, we're usually doing it for oxygen, because oxygen is sometimes a part of more than one chemical, and so you need some weird fraction to get there. But that's like a shortcut in just getting everything balanced. This would be changing the coefficients so that things cancel, not necessarily looking to balance them. Good question. All right, let's look at this problem. Let's calculate the heat of reaction. Oops, I already started wrong. For ammonia with oxygen forming nitrogen dioxide and water. This is technically another combustion reaction because we're burning with oxygen. That's an interesting one too. We want to know the standard heat of reaction for this. Is it balanced? What's a coefficient I could add in balancing this problem? Where do you want to start? A 2 in front of NH3, which will double the nitrogens on the left, offset it from the nitrogens on the right, and it'll double the hydrogens on the left, which also doesn't fix the hydrogens on the right. I've got 3 and 2 for my hydrogens. 3 and 2 will never be equal, so I can look for their lowest common multiple. If I can get hydrogen on both sides to be equal to 6, I just need to add whatever coefficient I need to get to 6. So 2 times 3 gives me 6. 3 times 2 gives me 6. My hydrogens are balanced. My nitrogens are unbalanced. So I'll take that same coefficient 2 and I'll add it in front of ammonia. Sorry, nitrogen dioxide. Ammonia's on the left. Now my nitrogens are balanced. I've got 2 oxygens on the left. 2 times 2 is 4, plus 3 is 7 oxygens on the right. What coefficient could I put in front of O2 to get 7 oxygens? 7 halves. This is an example of using that fraction. Valid? No. Shortcut. Now I multiply everything by 2. 4 moles of ammonia react with 7 moles of O2 to give 4 moles of nitrogen dioxide plus 6 moles of water. Fair? All right, I'm going to write my heat of reaction equation with 2 different colors so that we can tell apart the 2 sides. Here's the products in blue, and I'll do the reactants in red. What I want you guys to work on is using the equation, the sum of the heat of formation of the products minus the sum of the heat of the formation of the reactants. All I want you to do is write out what you would need, and then I will get you the values to plug in. So set up the equation that we have here for the actual chemicals of interest. Whose way am I in? Do I start with my products or my reactants? Products. So I need to take 4 times the heat of formation for NO2 and sum that with 6 times the heat of formation for H2O. Because the heat of formation specifically says how much energy is required for 1 mole of whatever your product is. And my equation needs more than 1 mole. So I need to multiply that heat of formation by multiple moles. And I'll subtract from this the heat of formation times 4 for ammonia plus the heat of formation times 7 for oxygen. Which of these 4 values will be 0? Why would the heat of formation for anything be 0? Can we define heat of formation again? The energy required to make the product from its constituent elements in their most stable form. Good. O2 is already in its most stable form, which means I don't need any energy to make O2 the way it is. So that goes for all metals in their elemental state, but metals in their ionic states do not have an enthalpy of formation of 0. It takes energy to make that metal be an ion. Remember, that's the ionization energy. We have to put energy in to pull the electron out of the energy well. So metals in their elemental state have an enthalpy of formation of 0. Our diatomic elements, H2, N2, O2, and the halogens, F2, Cl2, I2, Br2. And then also things like carbon in its graphite form. Actually, carbon in its diamond form is not its most stable form. It takes a lot of energy, high pressure to get there. Sulfur as a S8, an 8-membered sulfur ring, is in its most stable form. So NO2 has constituent elements that it can be made from. H2O has constituent elements. NH3 has constituent elements. O2 is its constituent elements. So the heat of formation for O2 is 0. All right, so let's plug these in. These are values that you do not have to memorize. These are values that would be given to you. Unfortunately, the problem that I found doesn't have them on them. So I'm going to use this table that RealChem has shown you guys before. I'm going to use that to get these. The heat of formation for NO2 is positive 33.2 kilojoules per mole. So that's 4 moles times 33.2 kilojoules per mole. Plus the heat of formation for water. I think we know this one. Where is H in the alphabet? Don't know. No, I wouldn't have known this one. Oh, it matters the phase. I didn't write any phases out. The phase that I was looking at was probably gas. So let's just do this all as gas phase. The problem that I had didn't give me the gas. That's the problem. So we'll go with gas phase for this. Again, you may be given 2 different phases of your chemical, and you need to know to use the heat of formation for the correct phase. So H2O gas, negative 241.8. Negative 241.8 kilojoules per mole. Notice heat of formation for for nitrogen dioxide, endothermic. The heat of formation for water, exothermic. So they have competing heat of formations. Heat of formation for ammonia. These tables are so rude. Negative 45.9 kilojoules per mole plus 0 kilojoules per mole for oxygen. From here, it's just a calculator exercise. $66.4 minus over 1,200 something. So here I get negative 1384.4 kilojoules for my products. And negative 183.6 kilojoules for my reactants. A negative minus a negative is a negative plus a number. Tell me what you guys get so I can see if my calculation worked out too. My left side's wrong. You all got that? Oh, you know what? I bet it's because I did something weird with my parentheses. Okay. Negative 1318, any decimal points? All right, and then here you're getting negative. Would we expect the heat of combustion of ammonia, burning ammonia, to be endothermic or exothermic? We would expect the heat of combustion to be exothermic. It's almost always exothermic. And we found that it was exothermic. The heat of combustion for ammonia. Oh, you know what? This is not the standard heat of combustion. This is the heat of the reaction that's given. But this is not the standard heat of combustion, because the standard heat of combustion has an important caveat. Per 1 mole of the combusted chemical. So if I wanted to write the standard heat of combustion, what would I need to do? Not 2. Divide by 4. So I would write NH3 plus 7/4 O2 gives NO2 plus 3/2 H2O. It would not be a true balanced chemical equation because it would have fractions in there. But that dividing by 4 then would give me something like negative 283 kilojoules per mole of NH3. That would be the standard heat of combustion. Sometimes the heat of combustion is the same as the heat of the reaction. We have that one here. the heat of combustion is the heat of the reaction. Because the rule applied, we had 1 mole of our reagent. But this time, the heat of the reaction is not per mole of ammonia. Fun stuff, thermochemical equations. All right. Hess's law, enthalpy, heat of formation. Any other questions on this? All right. Let's move on. By the way, today, I may not take a break. I feel like this is all your time. So if you feel the need to get up and move your legs, take a break, feel free to, but I think I'll probably just keep going so we can try and cover as many topics as possible. Oh, I crossed out calorimetry, but we didn't do calorimetry. Okay, there are a lot of calorimetry problems. We've talked about how you could take a chunk of something and either heat it up or cool it down, and based on the heat capacity or the specific heat, you could actually figure out how much heat is needed for that heating or that cooling. But we also talked about how you can put something like that into a solution, and you can measure the increase or the decrease in the water temperature and use that to inform about the something that's been put in there. But we also talked about how you can run a chemical reaction and measure the increase or the decrease in the temperature of the water and apply that back to the heat of the reaction. So I found a problem that actually uses a little bit of this heat of formation material, and I want to apply it into an enthalpy problem. So here's the question. Oh, maybe this wouldn't. I think this will work. What temperature will the water be? Oh, let's be more specific. Will a 100 gram water sample be after 40 milliliters of 0.2 molar ammonium hydroxide are reacted with 200 milliliters of 0.1 molar ammonium carbonate, starting at 25 degrees C. And then we're given this table. We're given the heat of formation in kilojoules per mole for hydroxide, bicarbonate, and carbonate, and water. Negative 230, negative 692, negative 677, negative 286. Okay, I know that's a lot to write down. Take your time. as you go through a test, I want you to think about how your equations sheet can help you. So look at all of the information that's here. Look at the questions that are being asked. And find equations in your equations sheet that can help you. What temp? All right, I need an equation that has temperature in it. In fact, I know something about temperature. So this tells me I want an equation that can tell me the change in temperature. I know what my initial temperature is. I want to know my final temperature. As I look through equations that have temperature, especially delta T, I see the calorimetry problems. Q equals mc delta T. Q is what? Q is not specific heat. C is specific heat. Q is heat. So I see an equation that says Q equals mc delta T. I know that I want to solve for delta T so that I can solve for T final. That's what the problem is asking for. That means I need to know M, C, and Q. Do I know M? I've got mass up here, 100 grams of water. Do I know C? I do know C, but it's not on my equations sheet. I need to know C for water, and I need to have that handy on my cheat sheet. C is the specific heat. The specific heat of water, 4.184 joules per gram C. It's not going to be on the equation sheet. It's not going to be given in the problem, most likely. It's one that you will have to remember and have ready. How do I know that it's the specific heat of water that I want here? Because I'm heating the water up. So I want to know, how will the water take in that heat? Okay, I have M and C. What is Q? How do I find Q? Typically, I would find Q by plugging this information in. But this time, I want Q so that I can solve for delta T. So there's another equation that I want, and it's on my equation sheet. It's not far after this equation. I want something that can give me Q. Q equals, there's a lot of right answers here, but one that's going to be the most helpful. Q equals delta H. Heat is enthalpy. Enthalpy is heat. Great. Now I need an equation that gives me delta H. Do I have an equation that gives me delta H? I actually just erased it. But given the information that I have a lot of information here. The enthalpy is the sum of the heat of formation of the reactants minus, the sum of the heat of the formation of the products minus the sum of the heat of formation of the reactants. That's where I need to use this. I also have to multiply by the number of moles, which means I need to know what the balanced chemical equation is. So after tearing through this problem, we now get to a point where we can say I need to write out an equation. What are my reactants? Sodium hydroxide. Water is not one of my reactants. Sodium bicarbonate. Good. What I have is a very weak acid, bicarbonate, and a strong base. What are the products of acid-base reactions? Water and acid. Or sorry, water and salt. So here's my water, H2O. What is left behind? Na plus. Carbonate. CO3, 2 minus. Keep in mind, hydroxide took a hydrogen. I'm taking H plus away from bicarbonate, and that's going to leave it as carbonate. CO3, 2 minus. Sodium bicarbonate balances 2 sodiums to 1 carbonate. Is it balanced? Oh, yes, you're right. The sodiums threw me off. Sodium shows up twice on the left-hand side in 2 different places. And then I need those 2 sodiums on the right-hand side in just 1 place. I was actually going to start putting coefficients in there. Good catch. That means that everything is 1 to 1. So when I plug in for the heat of formation, I'll take my products, water, times 1. That's negative 286 kilojoules. Plus carbonate, that's negative 677 kilojoules. And I'll subtract my reactants, hydroxide, that's negative 230 kilojoules, plus bicarbonate, negative 692 kilojoules. Easy? Easy. Plug it in. Yeah, why aren't we doing anything with the sodiums? Because the sodium is a spectator ion. The sodium is not changing. It started as Na+, it ended as Na+. There's no change going on with the sodium. We could add the sodiums in. We don't know what it is. Maybe the heat of formation for sodium is like 100 kilojoules. So I'll add 2 times 100 here and 2 times 100 here, which means that they'll actually just cancel each other out. So I don't need the heat of formation for sodium because sodium is not going through a chemical change here. I really only need the heat of formation for the chemicals undergoing a change. That's a great question, though. All right, what do you guys get when you plug this in? Negative 41. Wow, that's so small. Yeah, that'll do. Negative 41 kilojoules. Don't forget your units. Delta H equals Q. So Q equals negative 41 kilojoules. So now I can take Q equals MC delta T, and I can rearrange it to say delta T equals Q divided by MC. What I want. Delta T equals negative 41 kilojoules divided by 100 grams times the specific heat of water, 4.184 joules per gram degree C. Any problems? Huge. Yeah, my joules are not in the right units. I've got kilojoules divided by joules, which do not cancel. So there are two changes I can make. It's totally up to you. Rewrite 41 kilojoules as 41,000 joules, or rewrite the specific heat of water as 0.004184 kilojoules per gram degree C. Which change are you inclined to make? Whatever you want. Tell me. I would do the same. 41,000 joules divided by this. Let's make sure that our units cancel. I've got joules divided by joules, and I've got grams times 1 over grams, which leaves me with 1 over degree C. Other words, degree C. So I get 41,000 joules divided by 418.4, just multiplying those two numbers together, and that should give me negative 98. Holy crap, that seems like a lot. Maybe I don't know, seems like a crazy number. Is that what you got though too? I'll be honest, I made this problem up a little bit. I took this information from something online and then I just added a math. So maybe I needed to add a much, much heavier, maybe this shouldn't be 100 grams of water. Maybe this should be, yeah, who knows? All right, but that's what we got. That's delta T. Delta T equals final temp minus initial temp, which means my final temp equals delta T plus the initial temperature. T final is 25 degrees C minus 98 degrees C. T final equals very, very cold solution. Oh, huge mistake. Big, huge. Oh. No, that's okay. I did do initial minus the temperature change, but that's because temperature change was negative. Otherwise, I could have said negative 98 plus 25. No. I made a big mistake. Alina. Not sig figs. Ah, screw it. Danila? No. It can be, the change in Celsius is the same as the change in Kelvin. It's just offset by 273 degrees. But their units are the same distance, the same amount. No, specific heat is is joules per gram. And that's actually on your cheat sheet. We did. Actually, the moles of reactants were all 1 to 1 to 1 to 1. So when I did this in delta H, we did account for the moles. But I did skip that part. No. You're close, though. We forgot a negative sign somewhere. We calculated the enthalpy of the reaction. Endothermic reaction or exothermic reaction? It's an exothermic reaction. This reaction is releasing heat. How should the water change to a reaction that releases heat? The water should warm up. Did my water warm up? How did an exothermic reaction freeze this solution? So, what are we forgetting? We're forgetting some specifics, which is that the heat of a reaction is opposite to the heat of the water. And that was never written explicitly anywhere on our equations sheet, correct? But that's the big problem with calorimetry problems. You analyze for your system, in this case, the reaction, and then you apply it to the surroundings, in this case, the water and the thermometer. So we forgot to flip the sign. And you know what tipped me off to that? The fact that this neutralization reaction, which those of you in lab ran this last week, and those neutralization reactions give off heat. The fact that this neutralization reaction froze my water doesn't make any sense that an exothermic reaction freezes the water. So I could plug that back in up here. Negative 41,000 joules is a positive joules to the water. That means I'm looking at a positive change of 98 degrees C. That means I'm looking at 25 plus 98 degrees C. This doesn't change the absurdity of all of this. But now I'm looking at a temperature of 123 degrees C. Supposedly enough to... Oh, I do know the problem. Jacob, you were right. I didn't multiply by the moles of the reactants. Man, you know what I tried to do was give you guys like a roadmap problem in this, and I jumped the roadmap. Am I really consuming 1 mole of sodium hydroxide? Man, we got to go back and change all the numbers. Now that the math is there, we just change the number and plug it all back in. How many moles of sodium hydroxide am I reacting? I'm reacting 40 mils of a 0.2 molar solution. That would be 0.2 moles if I had 1 liter. Do I have 1 liter? So do I have 1 mole? I'm sorry, 0.2 moles? If I have less than 0.2 moles, do I even have 1 mole? No. So this whole process is actually releasing a lot less energy than what I calculated. I have to take 0.04 liters of sodium hydroxide and multiply it by 0.2 moles per liter, which gives me 0.008 moles of sodium hydroxide. Is that what you've got? Oh, bummer. Dang it, we were just at the end too. If it can happen to me, guess what? It can happen to you. Oh, but there could be an answer like that. So when you get on the test, I want you to have the same chemical intuition, which is, wow, this reaction is really boiling the water? You know what sodium bicarbonate is? Baking soda. And sodium hydroxide is lye. So if you mix this stuff together, would you really expect it to start boiling? Maybe get warm, but boil? That would be a lot. So that was a good tip-off that this is an insane number, and that's because I'm not providing 1 mole of these reagents. I'm providing 8 millimoles of a reagent. And 0.02 liters times a 0.1 mole per liter solution is 0.002 moles of bicarbonate. Oh, you wanted to do limiting reagent and excess? This problem was all inclusive. I just didn't plan for that. I have 0.002 moles of bicarbonate and 0.008 moles of hydroxide. Will all of them be consumed? Which one is limiting? These chemicals react 1-to-1. So we could use our skill in limiting and excess reagents, and we could take these moles of reactants and bring them to the same product. How many moles of water can be made from each of these? Well, this can only make 2 millimoles of water, and this can make 8 millimoles of water. Can I make 8 millimoles of water? I'm limited to 2 millimoles of water. So just because I have 8 millimoles doesn't mean I'll make 8 millimoles. Yeah? Does that make a difference? Yes, it does. Yeah, that was a good catch. I was just assuming it was 20 mils, but it wasn't 20 mils. It was 200 mils. Good catch. Oh, okay, so that's 0.02 rather than 0.002. Now what's my limiting reagent? I could make 8 millimoles of water, or I could make 20 millimoles of water. How many millimoles of water can I make? Just 8. How many moles of bicarbonate will react? Just 8. I have 20 millimoles of bicarbonate, but only enough hydroxide to react with 8 millimoles of bicarbonate. Okay, so this is where Jacob's correction comes into play. We need to multiply these values up here by 0.008 moles. So that's 0.008 moles times negative 286 kilojoules per mole. Let me ask you this. Do you want to go through and see the math, or do you see how we handled the limiting reagent aspect of it? Should we move on from this problem, or should we finish it? It's just going to be calculator exercise. We're just going to get a smaller heat of reaction, which is just going to give us a smaller temperature change, which is just going to give us a more reasonable final temperature. Do you want to see it? Raise of hands. Do you want to move on to the next problem? Okay. Jacob, thanks for catching that. Would have been lost without you. Are we good on calorimetry? We fell into one of the most common pitfalls, which was forgetting to change the sign when going from system to surroundings. That is one of the most common pitfalls. I wanted you guys to be aware of that. I fell into it accidentally, though. And you might too. Oh, there was another aspect about the final that I wanted you to think about. I know that you all have a lot writing on this exam. So when you get in there, into this weird space surrounded by a bunch of other students, and you've got a clock ticking down and you've got these hard problems sitting in front of you that you've never seen, it can be really easy to just overstress and overthink what you're doing. You've got 3 hours for the final. So take a deep breath when you run into a problem like this. Think about all of the different aspects and just take your time. If I could give you any piece of advice, it would be try to spend all 3 hours on the final so that you don't feel rushed at all getting out of there. Be fine making mistakes so that you can come back and try it again. All right. We did talk about lattice energy. So, do we want to talk more about limiting and excess reagents? Whose question was that again? Do you want to talk more about them? Was this context enough? Are you sure? All right. But if somebody else comes up with another reason they want to look at limiting and excess, just let me know. Okay, let's move on to some redox problems, and then we'll talk about compounding IMFs and VSEPR. Let's start off easy. What chemical here is the oxidizing agent? Can someone define what an oxidizing agent is? Correct. The oxidizing agent is the one being reduced. Oxidation is loss, which means the oxidizing agent is the one taking electrons, the one causing a loss of electrons. The oxidizing agent, the one doing the oxidation, is probably oxygen. Thus the name oxidation. This process of chemicals losing electrons was named for the fact that they give electrons to oxygen a lot. So that process of losing electrons is the process of becoming bonded to oxygen, oxidized. So oxygen is our oxidizing agent, which means that oxygen is oxidized or reduced. Reduced. Now I want you to think literally and figuratively about which element here is being oxidized. Literally, which element gets bonded to oxygen? Both of them. Both get bonded to oxygen. But are they both oxidized in the figurative sense, meaning their oxidation state has changed? That's where the rules for oxidation state, the common trends for oxidation state, that comes in handy. You'll have to come in here and actually make some analyses about those elements. What we do know is that ammonia is being oxidized, but we don't know if it's the nitrogen or the hydrogen inside of there that's being oxidized. So let's review how we determine an oxidation state. Also, and I'm not happy about this, oxidation state, which is the state an atom is in regarding how it has control over the surrounding electrons, is also the same as the oxidation number, meaning the value that we use to describe an element and its control over its electrons. And I say control over electrons because this has to do with electronegativity. The oxidation state for ammonia. I take all of the bonds to things that are more electronegative. That would be electrons pulling, atoms pulling electrons away from nitrogen. How many bonds does nitrogen have to more electronegative atoms in ammonia? 0. I add to that the number of bonds that nitrogen pulls on from less electronegative elements. 3. And I give that a negative number because nitrogen owns those bonds. So I get a positive 0, a negative 3, and then I sum with that the formal charge on the element. What is the formal charge on nitrogen? So the oxidation state is the sum of bonds to more electronegative atoms minus bonds to less electronegative atoms. I say minus because that gives us a negative number when that atom owns the electrons, plus whatever the formal charge is. So you have to know how to calculate formal charge to be able to do this. And I want you to be able to distinguish formal charge from oxidation state because they seem very similar. They're not the same. How do I find the formal charge? And this is on your equations sheet. So as long as you know how to use that equation, you're in good shape. Valence electrons minus lines plus dots. Valence electrons for nitrogen, 5, minus 1, 2, 3, 4, 5. 2 dots, 3 lines. 5 minus 5 is 0. So for nitrogen, I got 0 bonds to things more electronegative, minus 3 things to less electronegative, plus 0. Nitrogen's oxidation state is minus 3. What is hydrogen's? Each hydrogen has the same oxidation state. What is hydrogen's? No? Each hydrogen's oxidation state is +1, not -1, because hydrogen is bonded to something more electronegative once. Hydrogen's oxidation state is almost always +1. Unless it's bonded to itself, H2, then it has no bonds to things more electronegative or less electronegative. Or unless it's bonded to a non-metal, or sorry, a metal, which is not common and we don't see it in this class at all, I think. There was a trick about oxidation states. The sum of all oxidation states in a molecule must be equal to its formal charge. +1, +1, +1, -3, neutral molecule, checks out. +3 and -3 cancel, I've got a neutral structure. Okay, now that we know this shortcut, let's look at H2O to try and decide for water. What is the oxidation state of hydrogen on water? And what is the oxidation state of oxygen on water? -2. NO2, which has a strange structure, are there formal charges in this structure? How do you know? Looks weird. Do you know what looks weird to me? Oxygen only has 1 bond. Oxygen likes to make 2 bonds. And I didn't actually show us our O2. I should have probably started with O2. What's the oxidation state of O in O2? 0. It has no bonds to more electronegative atoms, no bonds to less electronegative atoms, no formal charge. So the oxidation state of oxygen here is 0. That is, its elemental state is 0. Here, oxygen has only one bond. That means that oxygen is actually holding more electrons for itself than it likes to. So this has a -1 formal charge. But NO2 is a neutral molecule. If I have a -1 somewhere, I must have a +1 somewhere. And it's not going to be on the oxygen that looks normal. Oxygen likes to have 2 bonds, which means it has to be on the nitrogen. You don't have to take my word for it, though. You can prove it. 5 minus 1, 2, 3, 4. 5 minus 4 is +1. Remember, that was important because in our oxidation state equation, I have to add in the formal charge on the atom. Oxygen bonded twice to an atom less electronegative, -2 oxidation state. Oxygen bonded once to an atom less electronegative and has a negative charge, steals electrons and has a negative charge, -2 oxidation state. Nitrogen bonded 3 times to an atom that steals its electrons. So that's +3. And it has a +1 oxidation state. So that's +4. Sometimes the questions will actually just give you this. They'll say, what is true of nitrogen in the following reaction? Nitrogen goes from -3 to +4. That's its change in its oxidation state. Nope. A double bond counts as 2, a triple bond counts as 3. That's good. Can someone explain to me again why this number would be positive, but this number would be negative? When I'm calculating an oxidation state, which is where I'm describing how much control an atom has around the electrons surrounding it, why is bonds to more electronegatives going to be a positive number? Meanwhile, bonds to less electronegative would be a negative number. Is it just too obvious? When the atom in question is bonded to something more electronegative, it loses those electrons, positive oxidation state. When that atom in question is bonded to something less electronegative, it owns those electrons, negative oxidation state. So that's a useful equation for just plugging in what your oxidation state is going to be. It's much like the formal charge equation, except you can see formal charge is needed there. Okay, can I answer more questions on redox? Good? All right, let's get this terrible question out of here that took so long and used every equation we ever learned about. Let's talk about compounding IMFs. Have you guys ever cooked with oil at home? Because I'll be honest, I didn't cook with oil much growing up, but I started cooking with oil a lot more recently. And Have you ever gotten the oil really hot? You don't know that it's hot because it's just sitting there. And then you put something in it, like vegetables, or that's usually what I put in it. And then it just starts spraying all over the place. What is going on? Why is it that putting something in there started making the oil spray everywhere when just seconds before it was just fine being at the same temperature? Any ideas? So it's things that have water go into the oil, and that causes the spraying. Did you want to add anything to that, Keon? It's the water that's freaking out, not the oil. The oil is well above the boiling point of water, but the oil is not at its own boiling point. So when you put water in, that water reaches its boiling point immediately, and that water starts boiling. That's what's boiling, not the oil. So what has stronger intermolecular forces? Water or cooking oil? Cooking oil must have stronger intermolecular forces because it can reach a higher temperature before it boils. It can reach a higher temperature before it's able to separate molecules from molecules. The strength between molecules is stronger than the strength between water. What types of intermolecular forces are present in water? Hydrogen bonding, which is really dipole-dipole. So if it has hydrogen bonding, it has dipole-dipole, and dispersion. Now you might not know the chemical formula for oil, but it looks usually something like this, where N is some number of chains, often like 17 of those chains in there or more. All right, so what type of intermolecular forces exist between oil? This little OH group here, that means that it can also do hydrogen bonding. The fact that we have a CO group means that we have dipoles in the molecule, so I can experience dipole-dipole. But a majority of this compound is nonpolar hydrocarbon chain, which means most of it is actually dispersion. By the way, water can do twice as much hydrogen bonding as oil. Both of its OH bonds can go on to make hydrogen bonds with other molecules. So it has twice as much hydrogen bonding per molecule as cooking oil. And hydrogen bonding, as we know, is the strongest of the intermolecular forces. So having twice as many, that's a game changer. And then in terms of dipole-dipole, the OH bond is actually larger in a dipole-dipole than a CO bond. So hydrogen bonding for water wins out, dipole-dipole for water wins out. Everything that we have should say water experiences stronger intermolecular forces, except for the experimental evidence, which says that oil has stronger intermolecular forces. This goes back to that analogy I gave earlier. Methane gas, CH4, only experiences dispersion forces. Also, most plastics that you interact with on a day-to-day basis only experience dispersion forces. So why is methane gas a gas, easily overcoming its intermolecular forces? And why do plastics stay as solids, not able to overcome their intermolecular forces? Plastics are incredibly long molecules. So per molecule, they have a ton of dispersion. And that's the same thing that goes on here with oil. Being such a large molecule means that it has tons and tons and tons and tons of little interactions, which can actually outcompete a small number of big interactions, right? I'd rather have 1,000,000 pennies than have a $100 bill. So you need to be able to both compare how intermolecular forces rank and understand that those intermolecular forces compound on each other, and the larger the molecule, the larger those forces. Another important consideration here would be looking at a series of chemicals like this, which is methane, trifluoromethane, and triiodomethane. I don't know why I put CI2. CF4 and CI4 both have polar bonds. CH4 has no polar bonds. But all three of these compounds, non-polar. Remember that we said in order for a molecule to be polar, it must have polar bonds, but it must also lack symmetry in some way. Maybe it has a lone pair on a central atom. Maybe it has two different types of bonds. These compounds on the right, totally polar. Totally non-polar, totally symmetric. Which means these three compounds only experience intermolecular forces in the form of dispersion, van der Waals. So if they're only experiencing the same force and they're approximately the same size in terms of length, I'm really just looking at the surface area that they have. The larger the molecule as a whole, the more space for it to interact with another molecule. We could do the same thing by taking hydrocarbon chains, propane, butane, hexane, octane. We know propane and butane are gases. Hexane and octane are liquids. They only experience the same intermolecular force, but that force is compounding because of a larger surface area. All right, thank you guys. When we come back, we'll look at these remaining problems. Wednesday morning, ACS exam from 10 to 10:50. And then review for the rest of the hour. Have a good day, guys.